Okay, you're already no. Okay. So hi everybody. So I'm Julie. I'm a postdoc in the brain simulation section. I did my PhD in Marseille on large-scale brain network models and its application to epileptic patients. So it's a pleasure to present today the framework of the virtual epileptic patients with TVB. I will start the presentation with some basic slides about epilepsy, and then I will go deeper into the application with TVB. Okay. So epilepsy is one of the most common neurological disorders, as 1% of the human population is affected, including between 4 and 800K in Germany. Epilepsy is characterized by the recurrence of unprovoked or spontaneous epileptic seizures. These are defined as brief episodes of signs and or symptoms, like alteration in behavior, some sensations, loss of consciousness, among others. And this is due to an abnormal electrical discharge in the brain. So you can see such an example in the figure below. That corresponds to a spontaneous seizures recorded in epileptic patients. Okay, so these epileptic seizures are characterized by an onset, a progressions composed of various sequences of fast discharges, panels with the blue hashtags, and spike and waves events, blue stars, and an offset. So these two generic patterns are found in a similar way across species. Here you have on the left side a seizure-like event recording in the mouse wool hippocampus, and on the right, hypothermia-induced seizure-like event recording in vivo in zebrafish. And so, like so you can see, like for the human seizures previously, they are sharing the same patterns. And we can also see this pattern across different brain regions. So epilepsy is actually a heterogeneous group of disease. Its classification is a key clinical tool in evaluating an individual with presenting with seizures. This classification is based on a 3-level diagnosis. As a starting point, so this classification starts with the seizures type, which is divided in 3 main groups, depending on the seizures onset. You have the focal seizures, so where the onset is confined to a restricted portion of the brain within one hemisphere. You have the generalized, so here the onset involves both hemispheres. And you have the unknown group of seizures that comprise, so for which the onset localization cannot be evaluated. Then we have the epilepsy type that is divided into 4 groups. Focal epilepsy, you have focal, multifocal, and disorder, but still restrict to one hemisphere. For the generalized epilepsy, it comprises the generalized seizures. And you have the combined, so it can happen that patients present both types of epilepsy, generalized and focal. And we have the unknown epilepsy. In that case, the clinician is unable to determine the epilepsy type due to an insufficient availability of informations. The third level corresponds to the epilepsy syndromes diagnosis, which refer to a cluster of features incorporating seizure type, EEG, and imaging features that tend to occur all together. The classification also informs the associated etiology and the risk of comorbidities. The etiology groups that have been recognized are the structural, genetic, infectious, metabolic, immune, as well as unknown group. For the comorbidities, it includes, among others, learning difficulties, intellectual disability, psychiatric features such as autism spectrum disorders, and mortality risk. The presence of etiology and comorbidity should be considered at each stage of the classifications, and this enables early identifications of the epilepsies for doing a diagnosis and appropriate management of the patients. Over all this type of epilepsy, about 60 to 70% of the patient can be treated pharmaceutically. But for the remainder, the only hope is either the resective surgery or something that is upcoming for the moment, brain stimulation. For the resective surgery, you need to know where the epileptogenic zone is. It is defined by the subregions that are responsible for the emergence of highly oscillatory and synchronized activity. This is what you see. So here you have an example of stereotactic EEG recordings. However, only a small percentage of this patient can access the surgery, only 10%. And on this 10%, the surgery still fails in about 40%. And even if this small graph is a bit old now, 2013 is still the number are still the same today, and we have no significant improvement of the surgery success rate in 50 years. So I will try to send a video. You will tell me if you're hearing the sound. So here it's a video of one of the patients in Marseille. She has been implanted with intracranial electrodes that I've shown you before. So the seizure starts a bit earlier. Here, what you see, the sequence of behavioral patterns. The patient coughs, she touched her nose, she's walking back and forth. The nurse is coming and trying to interact with her in order to see to what degree she is capable to interact. And we arrive at the end of the seizures. Okay. And here you can see the corresponding time series of the previous recording of this specific patient during seizures. The seizure starts here in the prefrontal lobe with the electrode FP and FO. Then you have an onset in the anterior cingulate cortex here, and also the premotor area, which means that the seizures spread and spread in the brain. At the behavioral level, here you have the axis for the behavioral level. So here at this, so it's when the patient starts to cough, touch your nose, cross the legs. The seizures propagate further to the temporal lobe, where the patient starts to sing and be jovial, and continue to propagate. So as you can see with these examples, it's like the epileptic activity is not restrained to only one brain area, but involves a widespread brain network, forming what we call an epileptogenic network. The epileptogenic zone, in which the pathological activity of highly oscillatory nature emerges, organize itself, and then we have seen that it propagates to other areas. It's what we call the propagation zone. So we are talking here of a network disease. And the fact that the surgery still fails can be due to the non-resections or insufficient modulations of the important nodes and pathways that characterize this epileptogenic network. So we need to study this network and understand them to improve the pre-surgery test tools, which have the objective to define the epileptogenic network in order to increase the success rate of this type of surgery. And so mechanistic understanding of the underlying brain dynamics of this network can be modelized by the use of brain network modeling approach. It's where TVB enters. So computational models can provide a framework for running in silico experiments to evaluate clinical hypotheses, for example, on the localization of the epileptogenic zone, perform a systematic virtual resections to reveal the best surgical strategy. It can also be used to new approaches to prevent abnormal brain functions by the manipulation of the parameters of the network and of the dynamics. But more importantly, this model can be informed with detailed patients' specific data in terms of large-scale anatomical informations. If there is a presence of lesions in the brain, some functional informations, so in the line of personalized medicine. Okay, so these sections is, so I will just remind a bit about large-scale brain network model that was introduced and presented last week by Denis. So it is, if you want, I think this this paper was already in your requirement of the papers. So it is based on the T. Okay, so we start directly. So large-scale brain networks model refer to the mathematical and computational models of the brain activity at the macroscale level that have spatial and temporal characteristics. The nodes represent the brain regions, which incorporate a realistic computational model of their internal dynamics, and the links refer to the connection between the nodes, that is, the interregional pathway that conveys the neuronal signals. These models are well suited to describe the generation of spatiotemporal activity patterns as observed in neuroimaging signals. And in addition, they can be individualized by informing them with subject-specific data. So the first thing we need to do is to reconstruct the structure of the brain. This workflow was introduced and presented in the two following papers. One from Misha, that is one of our members, and will have a talk about it later in the virtual course. And the other one is from Timothée Proy. So I won't go into details because you will have 3 talks. So Leon Martin will introduce the basics for the MR imaging, as well as for the parcellations, and Misha will present you the pipeline to get to extract and reconstruct the structural connectom specific for TVB. But just so here it's an overview of the pipeline where you have your anatomic, your structural imaging. Here you will have some main processing steps and how they are relating to each other. And in the last row, you get your input file for TVB. The main process to remind, so from the T1 scans, we divide the brain into brain areas or region of interest according to a given parcellation scheme, while the cortical surface is represented by a triangular mesh. And then the connectivity is given by the tractography based on the diffusion MRI. And finally, we can structural connectom is generated comprising 2 matrices, the weight matrix that correspond to the strength of the connections, and the track length matrix that correspond to the distance between the brain regions. So you can find our pipeline online on the eBrains research infrastructure. And Misha will, I suppose, will present you these tools. Okay, so once we have integrated, we are creating our brain avatar and the structure of the brain. Now we need to put a neural mass model on each brain area. So the neural mass models account for the global activity of the underlying networks of neurons. So these models can be physiologically inspired, like here. So in these models, the variables represent the average activity of a discrete set of neurons populations within the brain regions. So for example, it can represent inhibitory neuron or excitatory neurons. But we can also have some phenomenologic models where the system models the specific dynamical properties of brain regions into simple couple differential equations without attempting neurophysiological implementations. So depending on the level of complexity you choose, there exists a large panel of models implemented in TBB. For epilepsy, I advise you to read these two, so these next sections for the construction of the model for epilepsy is based on these two papers, Girsa in Brain in 2014 and Proix in the Journal of Neuroscience in 2014. Okay. So as observed in many types of seizures, they are characterized by an onset, the various sequences of fast discharge and spike wave events, and an offset. And these fast discharges and spike wave events define the basic building blocks for the seizures-like events. So we will start from these basic building blocks to create a model. Okay. So the fast discharges necessitate a first population with at least two state variables, x1, y1, due to their oscillatory nature. For the spike wave events, they comprise a large amplitude spikes followed by a long-lasting wave component, which represent a large class of systems collectively called excitable systems that necessitate a second ensemble, two state variables, but we also need one additional state variables that that is acting on a very slow time scale, slower than the spike wave events. And it is necessary to capture the time course of the alternating sequence of seizure-like events. So between the anterictal, between seizures, and the ictal state seizures. Also, based on the observation of the data, the fast discharges are either not present during the spike wave events, or it is only present during the wave but not the spikes. And these features define a directional link between the two populations that will be captured later via a bidirectional coupling. So the ictal states represent a clear departure from a normal state, a normal baseline behavior. And this transition from this normal state to a seizures and back constitute two bifurcations. So we have the onset bifurcations from the normal state to the seizures and the offset for the back. So based on these features, we can identify all possible bifurcation combinations and develop what we call a taxonomy on seizure-like events, and then discuss the most prominent class. So in the experiment, the onset of the seizures is characterized by the abrupt appearance of fast discharges. And these transitions, this transition is limited to either a subcritical of bifurcations or a saddle node bifurcations. However, the saddle node bifurcation requires a baseline shift of the measured time-dependent variables. And in our experimental data, we systematically observe a DC shift from the baseline field potentials. So the seizure onset corresponds to a saddle node's bifurcations. So from normal state to the fast oscillations. And we have this DC shift. When we progress toward the offset of the seizures, we also have a DC shift back to baseline. Only the fold limit cycle and the saddle homoclinic bifurcations show DC shift at the bifurcation point. However, for the fold homoclinic bifurcations, for the oscillations, it maintains a constant frequency toward the seizure offset, which is not found in the majority of the experiments. So we identify the bifurcation offset as a saddle homoclinic. And this type of saddle node bifurcation, homoclinic bifurcation class are called the square wave burster. We just pass this, okay. So now we have identified the bifurcation onset and the bifurcation offset. And we know this is this square wave burster. And it exists already typical models of this type of bursters. So here, the first it is represented by, so the first population has been chosen to be the Inmarsh-Rose model. For the second populations, it was chosen, so they use a normal form of an excitable system with a saddle node on invariant cycle bifurcations. This type of bifurcation allows to generate the seizure, the spike and wave discharges, but also the interictal spikes. This full model has been modified. So we recall earlier we have to introduce some coupling. So we have the function f1 here and the function f2. So this linear inhibitory coupling from population 2 to 1, and the low pass filter excitatory coupling from 1 to 2 So it is for the fast discharges to appear only on the wave part. We have also a negative feedback in the second population from the variable Z. And this allows to bias the preictal spice toward the seizure onset. And based on the recording, the local field potential is related to the total activity x2, so from the second populations minus x1. So here you have the simulations of this Epileptor model, the time series. In red, it's the Z variable, the slow permittivity couplings. And here you have empirical seizures. One of the most important parameters in the Epileptor model is X0 here. So these parameters control the excitability of the node, or what we call the tissue epileptogenicity. So for a node below a specific threshold, the epileptor does not trigger seizures. I said not epileptogenic, it is in its healthy state. But when I cross the threshold, the epileptor can trigger seizures, and it's said epileptogenic. Okay. The virtual brains are then built based on the mutual interaction between the neural mass model, coupled through the underlying. Here the big G is a structural connectom, and here is a coupling functions. So this is a general evolution equation of a brain network model that you already seen last week. So here is the neural model. Here you have the global connectivity, so coming from the social connectivity and undergoing time delays here. And we can also, the equation can also capture external inputs such as noise or stimulus. So in Epileptor, when embedded into a brain network model, the nodes are connected each other via the permittivity coupling, so on the slow variables. So why on this slow time scale? It's because it was shown that it allows the spread of the seizures through the network by recruiting regions that are not in the epileptogenic zone. So each network node capacity of triggering seizures will then depend on its excitability value, so the parameter x0, but also on its connectivity with the other nodes. So we just, I don't know, just show you. Is it this one? Okay. I will show you now the Jupyter notebook to model a simple epileptic brain. So you can find the tutorial either in your, if you have downloaded the TVB distributions, you have a demo folder. You can find them also on the TVB documentation website. So here you have the possibility to explore the epileptome model and visualize the bifurcation I talk about. As it is a complex model, so with high dimensions, you can choose the state variables you want to visualize. You can also here modify the parameters and see how the system behaves depending on the value of the parameters. So to simulate with TVB, you need first to choose your model. So here the epileptors. Here, and you can define the excitability for the regions. So either you put all the regions at the same excitability, but you can say, okay, these regions are more excitable than others. Then you have to define the structure of your brain. So the structural connectivity is important here. And then you define the interaction through the coupling functions. Here you define the integration scheme. You can choose a different which monitor you want to use. If you want to observe at the source level or at the sensor level, you launch your simulations, and then you can observe the time series. So here it's okay. It's at the source level, so the direct output of the simulators, the local field, it was like local field potentials. And you can see that majority of the regions are in a healthy state. And you can observe the regions we have defined above that are more excitable than the others, and you see that they are triggering seizures. And here it with the EEG monitors with a selected, now with all the sensors. And here the SEEG. Okay. I invite you to test these demonstrations. So now we have a specific model to simulate epilepsy, but now what we want is to simulate the specific patients. So this second section is based on the paper Gersay et al. From 2017. So in these patients, okay. So in these papers, they use a specific patient. It is a female of 30 years old from the clinic in Marseille, and she has a bitemporal lobe epilepsy. Here you can see the SEEG recording of these patients. And the dynamics are roughly between 2 and 4 minutes. On the top row, you can see a simple seizures, which start locally and stay locally. So the seizure start in the right hippocampus. So you can see with the electrode B here. On the middle row, you have a complex seizures, which means that actually the seizures still start here in the right hemisphere, but then it propagates to the other hemisphere. On the left hippocampus, so start here, the left hippocampus, here, B prime, and it propagates in the temporal pole with so here with T B prime and TP, but we don't really see, and in the hypothalamus. So there is a propagation from one hemisphere to the others. In the last row, it is a seizure that was stimulated. So they stimulate the left hippocampus here. And the seizure was triggered, spreading to the remainder of the left temporal pole and the hypothalamus regions. Okay, so we will refine. So from this patient, we have the structural connectum, but we will also refine his brain. For example, this patient has a positive MRI with a hypothalamus hematoma, which is a neural mass connected to the hypothalamus, so the violin area here. So this anomaly is reconstructed via the pipeline and integrated into the equations here. So on the first variable, so this is the state equation for the anomaly, for the hypothalamic hematoma here. And on the first variable, we integrate the local connectivity of the node. From the pre-surgery informations, we also know the hypothesis of the clinician about the epileptogenic network. So this gives us a setting of parameters in this table here. So the epileptogenic zone in red, so correspond to the right hippocampus, the left hippocampus, the left and right hypothalamus, and then the propagation zone here in blue. So these parameters have been set according to, of course, the region involved with the seizures, the seizure length, the length of the time delays before recruiting another regions, but also the seizure frequency in each regions. And to reconstruct fully the patients, so the only recording we have from this patient is the SEEG. So we will use a forward model to reconstruct the to build and model the SEEG recordings. So here are the needles that were introduced in the patient's brain. So they placed 8 electrodes on the left hemisphere and on the left hemisphere, and 2 others in red, 2 others in the right hemisphere. Okay. So to compute the SEEG activity, because the direct output of TVB is the source activity, so the local field potential. So how do we compute the sensor activity? So in TVB, the regions are projected to the surface using the region mapping matrix. So it would tell you, for example, for the green area, you can see the vertices on the surface, the triangle mesh. So this matrix will tell you to which regions the vertices here belongs. And once we are on the surface level, we are then projecting again, but this time to the sensors using a projection matrix. So I won't go into detail, but just to know that we consider each point on the surface, so each vertex is considered as an electrical dipole. And from this, we can use an analytical dipole approximations and compute this projection matrix or potential electric to compute the SEEG. So here I will show you this type of simulation, maybe here, or is it here? Is so this notebook, you can find them on the eBrain research infrastructure. Here it's for a specific case I will briefly talk to you in a bit. So here we have a specific patient. We import structural connectivity. So here you have the structural connectivity of these patients. For a better visualization, it was normalized here. They plot the connectivity strength, the structural connectivity strength for each regions. Then, based on the pre-surgical evaluation of these patients, we some regions have been defined in the epileptogenic zone, others in the propagation zone. So we are creating an epileptogenic network. To compute the SEEG recordings, we need to compute the projection matrix that allow to project the vertex on the surface to the sensors. It is also called gain matrix or lit field matrix. Either you already have it or TVB can compute it for you. Here it's a represent of two types of gain metrics. The VR was computed from the equation I've shown you. So this type of matrix is based on the distance, but also on the orientations. The other one was computed differently and was based only on the distance. Then we set up the Epileptor. So why 6D? So actually, in TVB, one of the coupling functions in the Epileptor model can be transformed into a 6 state variables. So it's easier for the integrations of the models. So here we define our Epileptor model. And here we set the epileptogenic zone and propagation zone. The coupling. Here we will visualize the direct output of the model. And then we can simply run this simulation with this simple command line. Here you can see the source activity. Here it's the X1 variable that is plotted. So you can see the seizure start in the 23 and in the 6, region number 6, and propagate in the region 27. For the LFP, so the combination of the population 1 and 2. So you see now the spikes. So you have the intellectual spikes and the spike-wide events. Here a zoom of this network. So only X1 or the combination X1, X2, so the LFP. And here you have the Z variable, the slow variables. So you can see that the seizures, so you have intellectual states, for example, here, and the seizure starts here. In this region, it starts earlier, here, and some other regions later in the propagation zone. And for the other region, it's even later. And here we have the reconstructions of the SEEG signal of the patients. So, okay, so now we have a model. We know how to refine it based on the data of the patients. But what we want is to compare now and optimize our model to best fit the empirical data of the patients. So what we can do is to systematically scan and vary other parameters that we believe are relevant. So here we have our model. So the model, the Connectom and our EZ hypothesis. We compute the forward solutions to compute the simulated SEEG, and then we fit with our data. this exploration is done through a parameter space. So we change parameter values within a range, and we explore the simulation results. So in TEB, it's possible to launch multiple parallel simulations. In the GUI, here you have the screenshot of the GUI interface. In the GUI, you can varying up to 2 parameters. In the Python, you can do as many as you want. So this screenshot shows you an example of this type of parameter space with 2 varying parameters. On the x-axis, this is the coupling parameters of my coupling functions. And here, on the y-axis, we are modifying the condition speed. And the colors correspond to the global variance. So we can, so we see where my system is the most variables with the red area. For our previous patients, in the paper, they systematically explore the parameter space of the global coupling strength, Ks. They also explore the local coupling of the lesions. And they use as metrics the seizure frequency. So here it is an example of the parameter space done in the paper. So here they investigate the left thalamus. They changes of the excitability in the epileptogenic zone, show clearly little influence of the number of seizures in the model. Here, however, it's another example for the region left parahippocampals, the epileptic in the propagation zone. And they choose this red dot for the best fit in the parameters. And here you have the results. So on the left, it's the empirical SEEG of the patients. And on the right, you have the results, the simulated SEEG. So on the top panel, we see the simple seizures that start in the right hippocampus, so the yellow regions, and the propagation stays there. In the middle panel, you have the complex seizures that start in the right hemisphere, in the right hippocampus. And in the left hemisphere, it starts in the left hippocampus. And then it continues and spread in the temporal pole. Here. And then you have also in the low panel the left hippocampus that was stimulating, and we observe a propagation pattern in the left temporal lobe, similar to the real SEEG recordings. And so we can see that our virtual brain model capture both simple and complex seizure state of the patient, but also the responses toward the stimulations. I'm just looking, see how it works. Okay. And here you have the comparison between the clinician predictions here. So in yellow, it's the epileptogenic zone. In red, it is a propagation zone. And here we have the result of our simulations, and it shows the distribution of excitability as used in our simulations with the parameter set identified previously. And the results are really similar. Here I will, so another and complementary analysis to fit the data is to compute the inverse problems. These sophisticated tools are now provided to perform this type of fitting in TVB. Maybe I have them in my presentation, but I don't remember. I will just show you. Okay. So this approach is called the Bayesian virtual epileptic patients. Bayesian because they are using a Bayesian inference to infer the epileptogenic regions. So on the eBrains collaboratory, you can find different notebook. Is where I was here. So here it was example of a simple forward solutions. You can see also from you have also the empirical data of patients to plot region electrode positions. So here you have the head of the patients and the electrode implanted. You have the real SEEG of the patients. But to study them, we use dipolar organizations. We filter them to study the frequency of interest and decimate the data to have less weight. We select the contact of interest, because what we want is not to infer the whole brain, but to infer using electrode when we see epileptic activity. And what they use as fitting a target is the log of the power spectrum of the contact. So here We don't have the SEEG, but it is the log power of the SEEG. And it is this curve we are trying to fit with the simulations. Okay. So no, we are not using the clinical hypothesis. What we want is to use the empirical data to find these unknown parameters and predict which regions are in the epileptogenic zone or in the propagation zone. And this technique is based on the following paper from Hashemi and Hall. So it's from last year in Neuroimage. And as I told you, it's called the Bayesian virtual epileptic patients. So here, the Epileptor model is reparameterized probabilistically. So here, this is our generative model of the Bayesian virtual epileptic patients. So X dot represents our system of equations of the epileptor with the state variables. U is the external input, like the noise. And we have the parameters here that we want to infer. And Y, it is our observation, the SEEG data. So the Bayesian inference allow us to obtain insight about uncertainty of our fittings, so makes probability statements about model parameters and deals with noise in the system. So this estimation of the probability is done using the Bayes rules or the Bayes theorem, which is simply the conditional probability formula that you should all know. The prior, so the prior p theta. So we propose a distributions of excitability value according to our knowledge about the parameters. So when we are looking so for example, for the epileptogenic zone, we know that the range will be closer to the critical point, while so Gaussian around the critical point compared to LC brain regions. The likelihood is the probability of obtaining the observed data given a set of parameters here. And the conditional and the posterior, it's the conditional probability distributions of the model's parameters given the observed data. So there is an algorithm called the Monte Carlo, which is a good approximation of the true posterior, but it's very computationally expensive. And one solution is a variational inference, in particular for the big data. So I won't go into the details of the mathematics. Here I will just show you the workflow of this BEVP model that aim to access the clinical hypothesis regarding the locations of the epileptogenic zone in our personalized whole brain model. So, as we have shown, we need first our MRI data to build the anatomy of our brain, parcellation, so the structural bone network. We have our epileptome model. So here, based on some timescale separations, we can reduce this 5-dimension model to only two equations, which reduce the complexity of the inference. Then it is our prior. So I have the okay. In red, you have the epileptogenic zone. This light green or yellow is the propagation zone, and HZ is the LC region. So you see, the LC region will be far from the bifurcation, so far from this critical point where I'm triggering seizures. The propagation zone, so it is close to these bifurcations, and EZ is above. So once we have all these elements, we have created our virtual epileptic patients. We can simulate them. And then using these inference algorithms, we compare this distance between these distributions using a metric of best fit, and either we reject or we validate. So it is so they're using a probabilistic programming language like STAN or PyMax3. And so more we have informations, and of course more significant model evidence, the more significant model. Here you have an example of a patient. So it is specific brain network of these patients. There is 2 epileptogenic zone in red, the 2-node propagation zone, and all the others it's LC regions. So here you have the curve of the node 7s, and it is the fitting. It is the observations, and over the estimations, so the best fit of our data, here for the propagation zone, and here in dark green for the LC regions. So here we can see that with these techniques we can infer all the individual parameters for each regions. And using this, we see that the epileptogenic zone is it in the higher values, and only for these regions and these regions. In the propagation zone, we have these regions, in these portions, and the LC region far from the bifurcations here. So all the examples, so you can, as I've shown you on the eBrains, you can have access of all the notebook for this, but I won't show them all. There are a lot. So what message we can draw from this course is that TVB offers a generalized underlying computational platform that allows for a wide variety of models to be expressed and to link them to brain imaging signals, like here for epilepsy, the SEEG recordings. Computational models allow mechanistic understanding of the brain function and the dysfunction from a dynamical system viewpoint. So here, with the Epileptor, so the Epileptor was constructed based on bifurcation theory and dynamical systems. And we show that by inferring our model with the patient data, we have a higher predictive value. And we can, with the last work done in particular in Marseille, we can hope to do a breakthrough in epilepsy research and improving the success rate for the patients having drug-resistant epilepsy. In particular, so using this approach of the virtual epileptic patients, it's currently in test in Marseille with a cohort retrospectively with patients. You can see some results on the right hand side of the slide. So they have, for the moment, 53 patients have been reconstructed with the deep learning and Bayesian's algorithms. And 25, so they have already 25 post-MRI. That you can see here in examples. And so in red, it is the epileptogenic zone. And they were able to estimate this epileptogenic zone for the patients that were seizure-free. And it corresponds, and the correspondence is as good as the clinical hypothesis. But it drops radically when the patient is not seizure-free. And here the VEP or these reports show a different epileptogenic network that were found from the clinicians. And I think we are almost done, and you can have some questions. I thank you.
Thank you. So,
and stop the recording.
Yes, I will stop the recording. Maybe before, can you just once again say where people can access the notebooks?
Yeah. So I will just
write it to the chat, and maybe for the recording we can just show it or just say. So you have to register on eBrains.
So we first, here it's a link to access the different tools available with the virtual brain platform. For example, as Denis maybe mentioned it last week, you can run TVB either by downloading the TVB distribution on the official website, but you can also access it through eBrains using the cloud. You can also use and perform some multi-scale simulations. But what I talk today, it is a TVB workflow for inferring a spatial map of the hyperexcitable zone in patient's brain. So for the Bayesian's virtual epileptic patients.
Okay, thank you. Now I stop the recording.